Good morning, everyone. We're going to do a quick walkthrough of assignment 15. This is a 7.3 target assignment. What do you guys think about the smaller assignments versus the larger assignments? Remember, the benefit to a smaller assignment is it's a little bit simpler, easier to think about. I'm asking fewer things. A more complicated assignment covers more targets, and that will really benefit some people. I think I might do a mix. So, like trying to offer some larger assignments when it's convenient, but then also like, hey, I just have a bunch of people that really need a 7.2. I'm just going to make a couple just straight up 7.2s. So I think that's where I'm going to go with it, but do give me some feedback so I can give what you guys need. So let's go ahead and walk through this problem. Standard basketball court has a central circle. So I did post a picture of it, but if you look at the basketball court, right, you have the this thing and then this. Oh, it's horrible. This thing and then this thing, and then in the center there's this circle, right? This circle right here, we have literally, I think in our class, like I've had you guys run around this circle. So I've had students try to run around this circle as much as they can. Now this is a pretty small circle. It's a 1.83 meter radius circle, if I remember correctly. Let's go look. Yeah. So you can't go super fast. It's a small circle. This is a difficult turn to make, and that's really what this problem is about, is how fast could you possibly go? So let's go through the problem and see what we think. So we have a student here. They're a 45 kilogram student, and we are told that they can get up to, what did I say, 135 newtons, excuse me, 135 newtons of friction. That's all their shoes can handle. Maybe if they had better shoes, they could get better. But you know, the shoes, you know, is that Michael Jordan? Is that still a thing? Whatever. That was when I was a kid. So provide a diagram of the situation. I think this is a reasonable diagram. I just want some picture of someone running in a circle. I think that's fine. And when we look here, we know that the person must have a net force going towards the center of that circle. So let's draw a free body diagram of it. So free body diagram, here's our kid. And our kid is, so here I'll draw it from the front now. So you have a person and they're running. Oh gosh, how do you draw someone running from the front? I think that's okay. Whatever, that's horrible. But if you imagine here that the ground is the gravity is pulling them down, and that there's a normal force pushing them up. And I think we can all agree on that. But if this person, and these two have to balance, right? This person's not accelerating up or down. What they're doing is they're accelerating towards the center of this circle. So as I have it drawn here, you can imagine like the center of the circle is over here. There must have some sort of net force towards the center of that circle in order to keep them moving in this circle. The only force that'll do that, I think, is down here, this friction. And if you've ever tried to make a turn on a basketball court and you've had your feet slide out from under you, you will have experienced what it means to not be able to make the turn you want because you don't have the friction. So yeah, this is where I'm going with this. This would be the free body diagram that I'd expect for someone like this. Now, obviously your orientations might be different, but ultimately what I need to see is that the net force on this kid is really just the frictional force. That's the only force here that could be possibly pushing this kid towards the center of this circle. So how fast can the kid run around the circle? Well, we know that the size of this friction is 135. And if we have 135 newtons of force, well, we do have a model that will tell us how fast they can go. So we know that the amount of force that you have to make you turn in that circle will be equal to the mass times the velocity squared divided by the radius. So I'm just going to start plugging stuff in. 135 newtons, well, that'll be equal to 45 kilograms times however fast they can go squared, all over 1.83 meters, excuse me. And I'm going to solve this for v squared. So to do that, I'm going to divide both sides by 45 kilograms and then multiply both sides by 1.83 meters. So 135 newtons times 1.83 meters, all over 45 kilograms. That'll be equal to v squared. So then I'll just take the square root of both sides. Oops. That'll just be then equal to v. Give me a second to run this through my calculator. Oops. that ruined everything. There we go. So 135 times 1.83 divided by 45, take the square root. I get 2.34 meters per second. Now, technically, if you're going to be a math nerd, you would know this is technically a plus or minus 2.34. That is reflective of the fact that we don't care what direction they are running around the circle. They could be going this way or that way. Direction doesn't really bother us. We just know that this is the most amount of speed they can possibly get. So we're fine with just keeping the 2.34, but I'd accept negative 2.34 just as well. So yeah, that's our answer for that part of the question. So far, not too bad. Now, how long will it take to go around the circle in one lap? So let's think about this. We have a circle. We know that our person is running at 2.35 meters per second around the circle. And we know that the circle has a radius of 1.83 meters. So as we go around this circle, well, we got to know what the distance is around. To get the distance around, it's so the radius here, we know that the radius, well, here, it depends how math theoretical we're going to get here. I know that if you have a circle, the diameter always needs to be multiplied by pi to get the actual distance around, right? So if the radius is half of the diameter, then it will have to be multiplied by 2 pi to make this work. So 1.83 meters times 2 pi should give us the total distance around. I get 11.5 meters. So this whole thing is 11.5 meters around. And we're going 2.35 meters per second. So if you're going 11.35 meters at 2.35 meters per second, I get you're just going to take 4.9 meters per second. So to actually write that out, I know that the position, the amount of time it takes for you to go that distance, be velocity times time plus initial position. If we're going to call this spot 0, and we know that they have to go to around to 11.5, that means 11.5 meters will be equal to 2.35 meters per second times t plus their initial position, which was 0. 11.35 meters divided by 2.35 meters per second, and this is a 5, not a 3.5, will give me 4.9 seconds. So as someone's running around that circle, fastest they could possibly do it is 4.9 seconds if this is their mass and this is the amount of friction that they can get. There was a bonus question of what mu is. That was just to sort of remind you back. If I was really going to be, super mean here, I could actually have just not even given you the friction. I could have not given you the friction or the mass, just given you mu, and you have to figure the rest out. But I'm not going to do that. So diagram of the situation is number 1. The free body diagram is number 2. The ultimate speed that they can end up going is number 3. And then how long it takes for them to do one lap, number 4. I hope this answers any questions you might have. I hope that you were successful. Please let me know if you need anything. All right, have a nice day, everyone. Bye.